Today, on Xena the Dan, we have something very awesome for you guys. Back in 2009, the company Microvision gave us the world's first pocket laser Pico projector, an incredible feat of engineering, utilizing 3 colors of lasers and a MEMS micromirror to produce a rasterized video image on any surface. 10 years later, we'll be taking one of these apart to get an incredibly deep and comprehensive understanding on how all of these systems come together to produce that video image. The other thing that I've done was to invite my friend over, Jeremiah, who runs the channel Join the Technicians. He has expressed a strong interest to see what's inside of one of these. So I told him, since I bought one, I'll let you take it apart. This will put his skills and my trust in them to the max. The one question I have is, how will he handle it when extra parts show up? Who knows? Let's find out together.
I've been wanting to get my hands on one of these Microvision ShowWX Pico projectors for a long time. Now this is a really interesting gadget. There's a lot of laser projectors that have been coming out on the market, and unfortunately they're not really taking off, but this particular one is sort of the flagship for the technology that everybody else copied.
I believe it's the first.
So they have a proprietary technology that has a tiny little 2-axis mirror that can steer the laser beam in order to create the scanned image on the wall. And so we're just taking a look inside. I have never seen this thing in person. This is my first time taking a look at it, and I am super excited to tear it apart.
So he did an excellent job with the presentation.
Oh, that's cool. So there's our output optical window. And we'll show you some footage of what that looks like in an operation later. Let's take a look at how we can get inside this thing. So we don't need any of that for now.
Nope.
Oh, cool. Inbuilt removable lithium-ion battery.
Yeah, it's a pretty nice sized battery too.
Doesn't pop out all too easy, does it?
Oh, it does.
Am I doing it wrong? All right. 4 hex heads, and it looks like it comes apart pretty easy. It's fairly lightweight. It's surprising. It doesn't really feel like there's very much mass to it.
It is really lightweight.
The battery, I would say, weighs about half as much as the whole unit.
So I believe this has one of the same OPSL lasers that I used for my laser pointer.
That is pretty slick.
This off the tray here.
Yeah, we don't need that around.
Magnets will probably help pick up the screws.
Nice, thank you. No doubt, that is convenient.
It really does help.
Yeah, they can stay.
But you're as excited for this as I am.
Alright, that would be, let's see, we've got, it feels like more screws down at the bottom underneath this sticker.
You get the screws.
I'll take that. Thank you. Alright, it should come apart now. And there it is.
Nice.
Pretty straightforward assembly.
Sure it looked like it.
Okay, so there's our IR in and out optical window. That's kind of cool.
You can grab it?
Yep, we can put that in the tray.
Cool.
Alright, so there's a sticker on the back attached to a ribbon cable, and the whole sticker has to peel off, which we have to do without putting too much pressure on the ribbon cable.
On the upside, it should be a lot easier to put a sticker back down. So much for that straightforward assembly.
Yeah, no kidding. I wonder how easy it is to release that thing. They got it buried between two boards. So, probably just easier to do it this way. Very carefully removing the sticker.
That's a load-bearing sticker, Jeremiah.
That is technically correct. It's got a very weird kind of foam metallized plastic backing on it. Conductive
weird.
static dissipative layer, which peeled off unfortunately when I pulled that ribbon cable, but it's got to be just to kind of spread the heat evenly. It looks like graphite. It looks like graphite on plastic, and yeah, it actually is. It's a piece of graphite layer that's got a plastic coating on it to help dissipate heat from the entire case, and it looks like they have metallized the inside of the chassis, and they've also laid a layer of aluminum tape down also to grab that heat and really spread it across the entire surface. And that,
all the little
and right there,
details.
that's
Nice.
why. So that must be our graphics processing unit. That's giving all our control signals, and it's got to get probably pretty warm. They even bothered to put a cell pad down for cooling the general power controller section, which is also pretty nice. So it's lightweight, it's plastic, it feels cheap as hell. But it looks like they spent the time bothering to get the heat away from the areas of the board, even though the chassis is plastic, just to keep the thing with an operational temperature. So they did spend some time engineering ways to keep this system cool while it was in operation. And that is a good sign.
I agree. It's the little details that really could give the quality away.
Well, if they didn't have it, it would run for a good 10 minutes and then it would thermally shut down or overheat.
Laser projector, now with built-in fog machine.
Laptop power supplies oftentimes use a very similar technique, multiple layers of aluminum, just to kind of cover the entire outside of the chassis, not only a grounding plane to prevent EM from escaping, because laptop power supplies are generally noisy, but also to spread the heat over the entire surface area of the plastic, just to get it out of the system, because generally they don't run more than 90 to 95% efficient at the top. So they do have quite a bit of dissipated heat at an average 65 watt power output. Okay, so those are our 3 internal screws, and I think that's all that's holding the entire assembly down. Cool, so the plastic cover comes off. Wow, that is a lot smaller than I was expecting.
Whoa.
That is an extremely thin laser assembly. So 3 colors of lasers and the XY gimbal are all inside this tiny little box, and that box is
Tiny.
less than 7 millimeters tall. So
I told you those were incredibly small.
Yeah, that is very, very small. That's pretty impressive. I just can't believe how thin it is. It's beautiful. So let's get the thing out of there. And they've got it adhered down gently to, again, looks like dissipate heat. So we should be able to gently peel that back up.
Man, this is a fan.
Oh, Jesus.
Jeez. Error.
Error. Well, so much for being gentle. At least she's here, she survived. Cool. Well, there's the entire unit. I'm kind of curious to power it up, just like this.
You do have a battery.
That we do.
Trust me, we're going to be getting some measurements on it. We have to power it up open regardless, eventually. Man, that's It's unfortunate that it's separated. Maybe it can be like super glued back down or something.
Doesn't need to be.
No, it's probably not. But
It's just sheer pressure, you know.
It's a bit more aerodynamic than I thought.
Either way, there's a very soft porous graphite. You could just lay it right back down and put tape over this, because obviously the board doesn't need it. So spacers. Okay, we'll grab the spacers. Set those with the other internal screws. We know that those are for separating the top from the case. And oh, cool! They're all the smaller size laser diodes.
Yeah, there's 3.8.
Cute.
It really interests me to see that the one of them, that looks to be a 647 nanometer red, which is a really interesting single mode wavelength. Oh, there's another little LED on the inside. Holy sh!
Oh, you can't see that from the outside?
Right there. No, that's covered by the case. Oh, there's two of them, an orange and a green.
So I wonder what it's doing. Is it waiting for input? Oh, the laser projector is on.
Nice.
Oh, cool. Want to hit the lights?
Yep.
So obviously it's dangling by ribbon cables and it's shaking quite a bit. Awesome. Oh, we got to smoke that up. And I can actually feel some of the parts getting warm here, but surprisingly, barely. I mean, I want to say that main processor that had the huge heat dissipation pad on it, it's not even really hitting 80 degrees Fahrenheit.
Might be more for the lasers too.
True. Yeah, what is the temperature on the lasers? You want to feel that? How are they doing?
They're warmer than Patrick is, but not by much.
It's surprisingly cool, isn't it?
Mm-hmm.
I really like this. Okay, well, for the next step, I think we're going to have to take a look at the inside of the optics. Alright, so we're going to take a look at what's on the inside of this unit and expose the MEMS, the micro electromechanical system. And we'll start by peeling the plastic off the side. Now, the way this is assembled, you can't actually access all the internal optics without tearing out either the photosensor or unsoldering or removing any of the diodes or the MEMS control cable. But
out the photosensor.
We can peel back the edge here without disconnecting any cables or unsoldering anything to expose some of the internal optics. And also get a look at the front head of the MEMS.
Yeah, I'm definitely going to want to get in some good video shots of that.
Yeah. So the first thing I'm noticing here is we have a very strong magnetic field being produced by this, what looks like a neodymium magnet, probably an N42 or something like that. We have an outside metallic structure that directs the magnetic flux, and behind that we have a very tiny mirror at the apex of those fields, and that mirror receives a small magnetic field by a printed coil on the back of it, and responds to the permanent magnetic field that surrounds it. So it can move back and forth like this, and it can tilt like this. Now we have all three colors. They're still on. Oh, and it just... Oh, they're back. So it's probably a little off-cal, but it did turn the other colors back on.
Let's open it and see what we get then. Oh yeah, you can still see very
clearly. And it doesn't trip out right away.
No, it doesn't.
Once it's so okay, cool. Well, now you should be able to show what's inside.
All right, so a little poker here. So we have the.
God damn it!
No.
It's going to sleep because there's no activity. No signal.
I'll just point those parts out in caption strip.
Alright, we can finally take a look at everything on the inside. So Patrick went ahead and unsoldered the two laser diodes. The sensor has been popped off. The tiny little thermistor sensor, that's this thing right here, that was also removed, and that just sits right here on the case to measure the temperature. Alright, so there's the entire optical assembly. And we can see both of our dichros for our blue and our red. and we can see our OPSL has a couple of correction lenses, a reflection mirror, and then it goes through an amorphic prism to slightly correct its optics more to make it, I'm guessing, slightly wider like the blue and the red, because it's got a significantly more narrow beam. It's pretty cool. They can steer the individual colors with these turnable prisms here.
Here is the Pico P display engine. It's a compact device with 3 lasers, additional optics, and the MEMS micromirror. First in the optical path is the Osram BL530, which is a 530 nanometer OPSL laser, and it's the same one I made my OPSL laser pointer with. This laser is an oddity, and it's because this projector predates the consumer market use of green laser diodes. OPSL stands for Optically Pumped Semiconductor Laser, which is very similar to a DPSS laser. The major difference is the doped pump crystal is instead replaced by an optically pumped semiconductor. In this laser, an 808 nanometer pump laser sends light through a correction lens and focusing lenses onto the OPS chip. The OPS chip converts 808 nanometers into 1060 nanometers. 1060 nanometer laser light then travels through a birefringent filter, which helps tune the light to only 1060 nanometers. After the BRF, the light is reflected off a dual-purpose optic and passes through a crystal. This crystal is periodically pulled lithium niobate and is held at a constant temperature by a positive temperature coefficient heater. Behind the PPLN crystal is a reflector, which reflects the oncoming 1060 nanometer light back through the PPLN crystal. The PPLN crystal is a second harmonic generation nonlinear optic, which converts 1060 nanometer light into 530 nanometers, which is green. The green laser light then passes through a dual-purpose optic, which turns the beam towards the aperture of the laser. Now that I have covered the OPSL laser, we can move on to the rest of the optical path. The green laser light leaves the OPSL and is sent through an expanding lens and collimating lens, which gives us a nice green beam. The green laser beam is reflected off a dichroic mirror and passes through an optic that filters infrared laser light and moves the beam lower so that it matches the level of the other lasers. Next is the blue laser diode, which is a 3.8 mm form factor. This laser is focused into a beam by a collimating lens and then reflects off a past green reflect blue dichroic mirror. Red is the last laser color and is produced by a red laser diode, which is also 3.8 mm. It's collimated just like the blue and is sent through a dichroic mirror that passes red and reflects green and blue. Both the blue and red laser have a beam alignment prism between the collimating lens and dichroic mirror. These can be rotated to allow for minor adjustments to the beam's position. After all 3 lasers are mixed into one beam path, they enter the beam steering portion of the assembly. The laser light travels past the MEMS mirror and hits a first surface mirror I have labeled Mirror 1, which reflects the beam onto another first surface mirror labeled Mirror 2. Mirror 2 then reflects the laser light through a prism, which turns the beam into the MEMS mirror. The MEMS mirror steers the laser beam as its color is modulated, which is reflected back through the beam turning prism. The last optic is for correcting any chromatic aberration, which is created by the beam turning prism. The beam turning prism gets thinner at the top, while the correction prism gets thinner on the bottom, which reverses any refraction caused by the beam turning prism, thus keeping the 3 colors together in a single beam. Here is the MEMS micromirror, which we'll discuss in fine detail later on in the video. There are at least 2 versions of the ShowWX, each with slightly different electronics. This one looks to be an earlier version and contains 2 printed circuit boards. The most notable IC on the inside of the ShowWX is the Altera Cyclone 3, which is an FPGA that handles most of the functions such as user inputs, graphic interface, and video source routing. Above the Cyclone 3 is a TL004, which I believe is an XVGA video controller. On the other side of the PCB, there are 3 RAM ICs which are used by the Cyclone 3, and also some custom Microvision ICs, but datasheets for them could not be located. The lower PCB contains an ISL 98002 triple video digitizer, which converts component video into digital video. This PCB also handles the voltage rail management, which provides the correct power to all the other components.
Alright, that should be everything back in place. Well, something's missing. One screw didn't get put back somewhere. Or more than one screw. Yeah, we're gonna have to take this back apart. I don't know where it's missing, but I'm gonna have to figure that out. Yeah. Do you know where these screws are missing from?
Where?
I have no idea. All I know is we have a lot more screws than are currently in place. I've only got 2 on the inside, and that doesn't seem right. I got one more riser that I can't figure out where it goes. Got me. That doesn't make any sense. Are they all from this?
Check the screws, see if they look to be the same.
Almost sure they're all from this. I'm just utterly confused as to where they came from. Yeah, they all look exactly the same.
No way. I think they have to be.
Well, all I know is they have, so no screws at all go in between these boards. And as far as I can see it, there's 1, 2, 3 screw holes on this side, 4, 5, 6, 7, 8, 9 on that side. And since no screws actually hold the 2 pieces of the board together, and there are no other screws holding anything else together, we should have a total of 9 screws.
How many?
That makes sense. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 screws.
Really, you have 2 extra screws? Apparently.
So where the hell did they come from? Something doesn't. Oh man, I fucking love it.
Oh.
That just makes 0 fucking sense.
Only one logical solution to this mystery. They came from that one instead.
You mother... God damn it. Son of a bitch. I took that whole thing back apart, you motherfucker. Man, you got me good with that.
Oh, I did.
You knew that was gonna throw me for a freaking loop.
Now, of course, I wanted to know exactly how these micro mirror assemblies worked, so I did the only logical thing and bought a bunch to experiment with. These micro mirrors are a modern marvel of engineering. The assembly is incredibly precise and is made with tuned accuracy to allow for dual-axis beam steering with only a single input. To fully understand how these work, we'll discuss the working principles involved, such as the drive signal, magnetic interactions, mechanical design, and how resonance plays a huge role in their function.
Let's take a look at the magical waveform that allows one coil and one signal to drive 2 axes. So I'll start by turning it on. Right now I have the probe wires connected directly to the driving coil. And we're booting up. So the first thing that we're going to see is our x-axis waveform running right around 18 kilohertz. And in a moment, it splits up. Let me show you why that's happening. So our y-axis waveform is this much larger one, and we have the 18 kilohertz carrier signal riding this 62.5 hertz main signal. So this is, again, this wider, slower signal here is our up and down. So it's a really clever thing that they did. One coil, because it has a lot of mass, won't respond to this really high frequency. But inside, the mirror assembly has a block of magnetic material on it that couples to the field produced by that bigger coil. And even though the larger coil doesn't move, it magnetically couples and makes the mirror assembly and the ferrite on the back move. So it is a super clever solution to use a really simple single input and get a lot of control out of it. Now, the even wilder part about this thing is none of this would work at all if the mirror and the coil were not perfectly tuned en masse to ride this exact frequency and amplitude.
Let's take apart a micromirror assembly and look at how a single waveform can drive two axes. On the back side of the front part of the mirror assembly is a pair of thin L-shaped magnets and a black piece of plastic. Under the mirror, there is a pair of thicker L-shaped magnets along with a center post for shaping the magnetic flux closer to the mirror. Sitting just above the mirror mechanism are two pieces of metal, which also helps bring the magnetic flux closer to the mirror. And on the back side of the mirror mechanism is where the ribbon cable attaches. This is the front of the mirror mechanism. The mirror is suspended by two torsion springs on the top and bottom, which link it to an electromagnetic pancake coil. Both the coil and mirror are suspended by two more torsion springs on the left and right. Connections for coil drive power and flex sensors are on the left. The entire mechanism is on an etched weakly magnetic silicon material. The magnetic coupling ring on the mirror responds to the magnetic field generated in the coupling ring on the electromagnetic coil by the electromagnet at 18 kHz, which moves the mirror on the x-axis. The electromagnetic coil itself responds to the magnetic field created by the four permanent magnets at 62.5 Hz, which controls the y-axis. Both axes are made to resonate like a tuning fork, and their angle of deflection is dependent on the current amplitude of their corresponding frequency.
After completely probing the MEMS mirror from the Pico Projector, we now have a clear understanding of how it works in the waveform. So what we did is we set up one of the MEMS mirrors, and I have here a 100 milliwatt green laser that is reflecting off the MEMS and to a mirror in the back of the room, giving us a bigger image of what's going on. And what we've done is we duplicated the signals using the program Audacity, and now we have full control of both the X and the Y axes. Now the MEMS mirror here is offset at 90 degrees, so the X axis is going to be up and down, and the Y axis is going to be left and right. Jeremiah here has Audacity running, and he's going to explain a little bit about what the waveforms do and how we've gained control over the MEMS assembly.
Alright, so we're going to see this waveform move up and down. Again, this is the x-axis, flipped 90 degrees, and we are going to pump in an 18 kilohertz waveform into it. Regular sine wave, and we can see good deflection. Now what I can do is shut that off and turn them both on. Now we have x and y axes operating both, and we have them set to the same amplitude, and we have a shockingly square waveform. This is giving us total control. Now for our y-axis, we are pumping in that same 62.5 hertz signal, and we tried to tune around with it a little bit, and it's really sensitive as far as the frequency goes. But once you get it tuned in just right, it's nice and stable, and we can go ahead and change the amplitude on these individual gains as well, and really screw with the image.
To drive one of these mirror assemblies, you will need two wires. A portion of the ribbon cable has to be scraped off to expose the copper for soldering. I have marked these areas with red marker. Here are the finished connections on mine, which connect directly to a mono audio jack. You won't get the full deflection with such a small input current, and I recommend using a low-powered AB audio amp to boost the current going to the coil.
So to give you a little bit of a better idea how we're actually controlling the micro mirror assembly, we've attached the oscilloscope directly to the audio input signal that we're feeding it from Audacity here. So I'm going to start out by playing just our high frequency x-axis waveform. You can see we're generating a line right now, and there's our 18 kilohertz signal on the scope. If I go ahead and play just our low frequency 62.5 hertz signal, and you can see that's being generated right here. That is now giving us our y-axis, and then we can turn them both on at once, and once again we get our square, and you can see that there's a sudden amplitude change where we have our embedded signal riding on that carrier, and we can again zoom in and see that signal real clearly. So it's not actually all that complicated. Again, we're just using that same two-wire input and driving it right off the headphone jack of the laptop.
10 years later, the Microvision ShowWX is still an amazing piece of technology. I would recommend getting one if you're a collector of video or laser technology. It does have its downsides, though. If you're looking for a practical projector, this is not the one for you, as it does not have any standalone playback functions, requires a proprietary cable to run off a VGA video source, and is not very bright. In addition to that, despite the box saying Amplify Live, the ShowWX also lacks a speaker. The color reproduction is a rather interesting experience. The color produced by the ShowWX is incredibly vibrant, though there is laser speckle that can be seen on the video. Overall, I'm impressed with the engineering and enjoyed discovering how it works. I hope you enjoyed watching this video and learning about how laser beam steering Pico projectors function. As always, stay tuned for more.
I haven't had anybody pull a prank on me in a super long time.
I had to do it, man.
I feel so special.
That's how you know I care. When you said, man, you got me, all I could think was, I really did.
You really did, man. That totally screwed me up.